This is Chapter 1, Part 2, Functions, Graphs, and Limits. We are now going to explore sections 1.5 and 1.6. 1.5 is limits and 1.6 is one-sided limits in continuity. I put these two sections together because they overlap so much and have to do with one another drastically. This is the beginning part of calculus for us. And so these ideas are going to be new. So definitely reach out to either the TMARC, the ASAC, or to myself for additional help and support. And then also reach out to your classmates to make sure that you have a great support system and people to work with and study for on these new ideas. So a limit allows us to determine the behavior of a function around a given point, even when the function is not defined at that point. So it's almost like what it's approaching. And it doesn't have to be defined at a specific value. It could still have a limit at that undefined value. So we can use a table or a graph to estimate limits, which is a tool used to describe the behavior of the function as the value of x approaches or becomes closer and closer to a particular number. For example, what happens to f of x equals 5x plus 4 as x gets closer to 2, but not equal to 2? So maybe there's a hole at 2 in the graph, and so it's undefined at that point. And so we have a graph given and also a table given. And so looking at this table, this value in here that's missing is a 2. I'm going to go ahead and put that in. I want you to note there's the x values and then also our y values, our f of x. And we are approaching 2 on the left side. So this is approaching 2 on the left. So this means that we are getting closer and closer to 2, but on the left side, which is a little bit smaller than 2 if you think of a number line. So we have 1.9, and then to get even closer to 2, we say 1.99. Even closer, we say 1.999. Likewise, we can approach 2 on that right side, and these are values that are a little bit bigger than 2. So I started this at 2.1. To get even closer, we say 2.01. To get even closer than that, we say 2.001. You did not have to use these specific values. You could have used something different, like 2.1 and then 2.015. So there's a lot of different values that you can use when constructing a table. However, this is usually the standard method and the standard values that they would pick as you approach a specific value. So you always need to look at the value as you're coming in from the left and also as you come in on the right. So to get those y values, or those f of x values that we see in our table, we substituted 1.9, 1.99, 1.999 into our function, which was defined up above, which is 5 times x plus 4. And we got those corresponding values. And you'll notice that it goes from 13.5 to 13.95 to 13.995. Likewise, on the right, as we get closer and closer to 2, on the right side, a little bit larger than 2, we go from 14.5 to 14.05 to 14.005. And so you'll see that these values, as we get closer and closer to 2, are approaching 14 also. So we can say that this value would be 14, since the left side is approaching 14 and that right side is approaching 14 for our y values. So we can say the limit of f of x as x approaches 2 is going to be 14. And this is going to be written, and we have some new terminology here with limits and a new way to write that. And so you'll notice they write LIM for limit. The x value is approaching 2, which is what we are asked to find. And we put our function here, which is 5x plus 4, which was defined up above. And then this is equal to 14, which is what we got down here in our table. Looking at the graph is another way to do this. And as you approach 2 from the left and from the right, you can see that This is approaching about 14. I know this is difficult to see on a graph, but that is approaching 14 also. And so we also have what's called one-sided limits, which would be just approaching just from the left. And so when x approaches the number from the left-hand side only, or when x is less than c, we're considering the existence of a left-handed limit, which is denoted, and you'll notice down here, x approaches c, and you'll notice this little negative exponent, and that means from the left. Similarly, when x approaches the number on the right-hand side, when x is greater than c, then we're considering the existence of a right-handed limit, and that's denoted the limit as x approaches c from the right, and that from the right would be this little plus up here of f of x. And then we say the limit as x approaches c of f of x equals L exists if and only if the left and the right-sided limit, so this is our left, since it's the limit as x approaches c with the little negative means left, is equal to the limit on the right. And L, that value that it's approaching, needs to be a real number. In words, a function f of x has a limit as x approaches c if and only if the limit from the right of c is equal to the limit from the left of c. And so we have an example right below this that says, find the limit as x approaches 3 of f of x, where f of x is equal to x cubed minus 3x squared over x minus 3 by creating a table of values. So I'm going to go ahead and create a table. So my table is going to have x values and f of x values, or our y values. And I'm going to go ahead and make a few columns in. I'm going to go 3 numbers from the left as we approach our value, and our value here is given to us as x approaches 3. So I'll put a 3 in here on my table. And then I'm going to have 3 values that are going to be larger than 3 in addition. So let's start with values that are larger than 3. So values that are larger than 3 would be 4, 5, 6, 7. All these numbers are larger than 3. They don't want to be that far away. So I'm going to say just 3.1. And the idea of a limit is seeing what happens as you get really, really, really close to that x value. So getting even closer, we'll say 3.01. And getting even closer to that would be 3.001. And yes, you could get even closer with 3.0000001. You can really see that behavior a little bit closer. From the left side, these are going to be values that are smaller than 3. So something smaller than 3 would be 2, would be 1, 0, even negative values. So a little bit too far away. I'm just going to say let's go ahead and start with 2.9. I need to get even closer to 3. So I'm going to say 2.99. And even closer to 3, we'll say 2.999. And so now what we need to do is use our calculator and substitute these x values in one by one. There's 6 different values here to substitute in into our function that we're given here. Now, note that 3 cannot be substituted into this equation. If you substituted in 3 right now into the circled f of x function up above, it would be undefined. If you notice that, the value of 3 would cause the denominator to not exist. So I'm going to go ahead and put down does not exist here. So it does not exist. So we write DNE, which is does not exist. So take a moment, substitute all these values in on your calculator, and we're going to write down those y values. And so the first one that we have is 9.61. And so now looking at this, as we approach 3 on the left, what is going on with our y values? They look like they're getting closer and closer and closer to 9. It looks like f of x is approaching 9. Likewise, as we approach 3 on the right-hand side, what is going on with our y values down here in our table? And you'll notice our y values are approaching 9 also. And so we're going to say that the limit as x approaches 3 of our function, I'm just going to call it f of x and not write the entire function. But since these two values from the left and from the right are equal to each other, I can now say that the limit as x approaches 3 of f of x would also be equal to 9. And that would be my solution. So yes, it is undefined at 3. However, I'm going to take the limit, and when you take a limit, you need to look at both the left and the right-hand side to see if they're equal, as stated right above this example. And so the limit exists, and it's equal to 9 because the limit from the left and the limit from the right both approach the same value, and that value is 9. The limit of f as x approaches a will not exist, or we can say does not exist, D and E, if 1, f of x becomes infinitely large, positive or negative. That is saying that as x approaches a, f of x is going to be approaching infinity or equal to infinity or to negative infinity. So for these cases on a graph, if we had a value of a here, it would be, as you're approaching it, maybe it's going up to infinity at a, or maybe down to negative infinity at a. And so this would be a case where we would say the limit does not exist. 2, we can say that the limit as x approaches a from the left is equal to L, whereas the limit as x approaches a from the right approaches m, and L and m are not equal to one another. So again, as we approach a, one of them is going to be approaching L, and one will be approaching m. And we can say that on the left side it is approaching L, whereas on the right of A it's approaching M. And so again, remember that in order for the limit to exist or equal, like we saw in the previous example, the left and the right sided limits must be approaching the same numerical value, and in this case they do not. And so whenever they do not match, we would say the limit does not exist. So the next example says use the graph of f of x to evaluate the limits. And so the first one that we have is the limit as x approaches a of f of x. And so for this, we would say this one does not exist because you can see that going to a from the left is approaching negative infinity, and a from the right is approaching a positive infinity. And so we would put down does not exist. For b, it says the limit as x approaches b of f of x. And if you notice at b, our y values do not match. And so it looks like as it's approaching b from the left, it gets close to 1. And b from the right, it's approaching 2. And since our left and our right side limits do not match, we would say this also is a does not exist, or D and E. The third one that we have on here is the limit as x approaches 0. Remember, 0 is at the origin. And so at 0, it looks like we have a hole down here at about negative 2 point something. But as you're approaching 0 for x from the left and 0 from the right, you'll notice that they match, and it looks like they're approaching about 2. We'll say negative 2. The limit as x approaches c of f of x, this is part D. If you look at that, you'll notice that as you're approaching c from the left, you're actually approaching 2. And approaching c from the right, you're approaching 0. And those two values do not match. And so this would also be a does not exist. The next thing that we have is algebraic properties of limits. And so these are good properties to know. And so this says if the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, then the following laws are true. So the limit as x approaches c of f of x plus or minus g of x would be equal to the limit of each of those, and then adding and subtracting each of those limits. 2, if you have a constant k being multiplied to a function, you can actually pull that constant k out in front of that limit and evaluate the limit of that function first and then multiply by k. 3 says the limit as x approaches c of f of x times g of x. You could take the limit of each of those functions independently and then multiply them together. And similarly for 4, but dividing. So the limit as x approaches c of f of x over g of x, you can take the limit of f of x independently and then the limit of g of x. And then this is also provided if the denominator is not equal to 0. 5 works for powers or roots even, since you can express them both ways, and it's stated in both 5 and 6. The limit as x approaches c of f of x to a power, you can take the limit and then take the power of the whole entire answer that you would have. And likewise the same with the roots for number 6. The limits of 2 linear functions, the next box right below. For any constants k and c, the limit as x approaches c of k is equal to k, and the limit as x approaches c of x is equal to c. So we have some examples right below. And for this, it says evaluate the following limits. So the limit as x approaches 2 of 4, this would be that first case that we have up here. And this would just be equal to 4. And if you were to think about this graphically, this would be the same thing as f of x is equal to 4, which is saying that your y value is equal to 4, which is going to be a horizontal line here. And as you approach 2, from the left and from the right on our graph, you'll notice that we're still approaching 4 for our y value. And so you can think about it in terms of a graph, or you can think about it in terms of those properties listed right up above. The next one that we have is the limit as x approaches 3 of x. And again, thinking about this in terms of a graph, this would be our f of x is equal to x, or y equals x, which if you were to graph this, you can see we would have a straight line that goes to the origin and is angled at about a 45-degree angle. And so this one is asking as x approaches 3, so here's 3, and as we approach 3, our y value is approaching from the left and from the right is also approaching 3. And you can also see this as stated up above. The limit as x approaches c of x is just equal to c. So this would just be equal to 3. The next thing that we have is how to evaluate limits more algebraically. And so what we're going to use is called the direct substitution property, so very important to know. So it says if p of x and q of x are polynomials, then the limit as x approaches c of p of x is equal to p of c. And likewise, the limit as x approaches c of p of x over q of x is equal to p of c over q of c, again, provided that the denominator is not equal to 0. So what we're going to do is we're going to substitute in that value as x is approaching into our function, and we would get p of c. And the same thing with the division one. In other words, we can use direct substitution on limits for all polynomials and rational functions with non-zero denominators. So we have an example right below that says evaluate the limit if it exists. And so using direct substitution, we can solve this. In addition, you could graph this to see what happens to the graph as x approaches 2. Does not look like a fun function to graph, you can also create a table of values. However, direct substitution is so much faster, and it's also more accurate than creating a table or a graph, because those are usually estimates. So for this, using direct sub, our value that x is approaching is 2. So I'm going to go ahead and substitute in 2 for our x values. And then working this out, we get 4 minus 1 over 6 plus 2, which works out to being 3 over 8. So this was a lot faster than creating a table or graphing this function. When using direct substitution, sometimes we arrive at values that are indeterminate and can't determine their value. So indeterminate is going to be a big word that we use throughout this course. And a function f of x is indeterminate at x equals c when f is evaluated at c and we arrive at an expression of the form 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity. We do have a few others that might show up, but these are the 4 main ones that we will see for this class. And so for these, we can't use direct substitution because these are indeterminate. So we're unable to use direct substitution at this moment. However, whenever you arrive at one of these indeterminate forms, we need to simplify first. So we need to simplify first. And once we have this simplified, we can try direct substitution again and hopefully arrive at a value and an answer from direct substitution. So right below this, it says when evaluating limits, sometimes we arrive at some unique answers, and so there's 3 of these. And so sometimes you arrive at 0 over a number. I want you to note that's not indeterminate. Indeterminate is going to be 0 over 0. Or we might arrive at a number over 0, which again is not indeterminate. Or we might arrive at 0 over 0, which is indeterminate. And so a lot of times students get confused with these different scenarios. So let's just write them out. 0 over a number would just be equal to 0. And then a number over 0 means that we're going to have some kind of vertical asymptote. And so this is going to either be positive or negative infinity. And I'll put down, we have a vertical asymptote. And so this is either going to be approaching infinity or negative infinity. The other one that we have here is 0 over 0, and this is indeterminate. And anytime we have indeterminate, we need to simplify. And so this is going to rely on our algebra skills. And so we need to simplify. And so this is usually the rational function can be simplified, or a table can be used to evaluate whatever it is that we're looking at for that limit. So we have some examples right below that say find the following limits algebraically and show clear steps. And so for the first one, I'm going to go ahead and just try to use direct sub. And if I get a numerical value, then we're good, we're okay, and we can circle it and say we're done with that problem. Remember, if we arrive at 0 over a number, we get 0. A number over 0, we get plus or minus infinity. And then if we arrive at the case of 0 over 0 or any other indeterminate forms, we must simplify the problem first. So for this one, for part A, it says the limit as x approaches 2 of 3x squared minus 2x plus 1 over the square root of 6 minus x. And so I'm just going to go ahead and substitute in our value for x, which in this problem is 2. And so we're going to have 3 times 2 squared minus 2 times 2 plus 1 all over the square root of 6 minus 2. From here I would simplify this. We have 3 times 4 minus 4 plus 1 over the square root of 4, or just 2. And then from here I would have 12 minus 4 plus 1, which would be 9, over 2. And so this is a numerical value, so that would be our answer. So we know that this function that we have, as x approaches 2, my y value is going to be approaching 9 over 2. So let's look at B. B says the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2. So again, we're going to try direct sub. And doing that, I'm going to have 2 squared minus 5 times 2 plus 6 over 2 minus 2. So right away I notice that we have an issue in the denominator. That is definitely going to be 0. So let's see if the numerator works out to a numerical value or also to 0. So we have 4 minus 10 plus 6, which is 0. And so right away this is indeterminate. And I'll abbreviate that there. So it's indeterminate. And this means that we need to simplify. So in order to simplify this, first of all, we need to continue to write limit as x approaches 2. You need to write this because it's a different numerical answer if it wasn't approaching 2. Like if it was x approaching 5, we wouldn't have ended up at this indeterminate form. We would have had a numerical answer. So it is important to write this. You will lose points if you do not continue to write limit when you need to. So looking at the numerator, I realize we can factor this. So multiplies to 6 and adds to negative 5 would be x minus 2 and x minus 3. And then our denominator was x minus 2. And so these x minus 2 factors will reduce. And we're going to be left over with the limit as x approaches 2 of x minus 3. And from here I'm going to try direct substitution again. And I'm going to have 2 minus 3, which equals negative 1. And so now we have a numerical answer. So again, anytime you have an indeterminate form, such as 0 over 0, or other ones that are listed up above, we need to simplify. And in this case, we had to factor, and our common factors reduced out. So at the top of the next page, we have C. And C says the limit as x approaches 9 of the square root of x minus 3 over x minus 9. And so again, substituting in our values, we would have the square root of 9 minus 3 over 9 minus 9. And if you note, I did not write limit for this because I substituted in the value. So once you've substituted in the value, you do not need to write limit. You notice the denominator is 0. The numerator is going to be square root of 9 or 3 minus 3, which is also 0. So this is going to be indeterminate, which means we need to simplify this. So simplifying this, we have to think of another way to deal with this. So right now we have the limit as x approaches 9 of x minus 9 and then the square root of x minus 3. And so for this, we're able to, two ways to do this. You can either factor the denominator, which might be a little tricky for some of us, or you can multiply by what's called the conjugate. And the conjugate is going to be the part that has the radical in it. And instead of a minus sign in there, we're going to have a plus. So the conjugate of the numerator will be x, the square root of that, plus 3. And then also multiplying the same thing to the denominator. And so multiplying the numerator, we're going to have the square root of x times the square root of x, which is just x. We get plus 3 square root of x minus 3 square root of x, and then minus 9 over, and I'm just going to leave this as x minus 9 rad x plus 3. And if you notice, your square root of x's times 3 would reduce, would sum to 0. And if you notice up above, we are left over with x minus 9. So we have the limit as x approaches 9 of x minus 9 over x minus 9 times rad x plus 3. And those factors of x minus 9 would reduce. And we have the limit as x approaches 9 of 1 over the square root of x plus 3. So from here, I'm going to go ahead and use direct substitution and substitute in 9 for x. So we have 1 over the square root of 9 plus 3, or 1 over 3 plus 3, or 1 over 6, which is the numerical answer that we would have for this problem. The next example we have is D. And D says the limit as x approaches 2 of 3x cubed minus 12x squared plus 12x, all over x minus 2 squared. So right away I can see that 2 minus 2 squared in the denominator is going to cause it to be 0, which is going to be an issue. So let's see what the numerator is when we substitute in 2. So 2 minus 2 squared, and then in the numerator we're going to have 3 times 2 cubed minus 12 times 2 squared plus 12 times 2. And substituting in 2, we get the denominator would be 0, and the numerator, when you multiply and add and do order of operations, is also going to work out to being 0. So this is also indeterminate, which means we need to simplify. So from here, write the limit as x approaches 2. The denominator is already factored as x minus 2 squared, but the numerator I can factor out a GCF first. That GCF would be 3x. We'd be left over with x squared minus 4x plus 4. From here we can still factor that numerator. And so we have 3x multiplies to 4 and adds to negative 4 would be negative 2 and negative 2. So we'd have x minus 2, x minus 2. And then our denominator here is x minus 2 squared. So in both the numerator and the denominator, we have 2 factors of x minus 2. So they would reduce out. We'd be left over with the limit as x approaches 2 of 3x. And so now I'm going to use our direct substitution property and substitute in 2 for x. When I do substitute this in, I stop writing limit. So it's going to be 3 times 2, or this works out to being 6. So we have 2 more examples that are dealing with these that I'm going to go ahead and circle. So circle E and F, and we'll look at both of these together in class. Long-term behavior is often a matter of interest in business and economics. The symbol infinity is used in mathematics to represent unbounded growth. And so we have what's called limits at infinity. And so this is if the value of a function approaches number L as x increases without bounds, which would mean the limit as x approaches infinity of f of x equals L. And if the value of a function approaches the number m and x decreases without bounds, so we're saying the limit as x approaches negative infinity of our function equals m. Graphically, limits at infinity represent horizontal asymptotes of a graph of a function. We have the reciprocal limit rules. So it says if r is a positive rational number and c is any real number, then the limit as x approaches positive or negative infinity of c over x to the r is going to be 0. So that would mean that denominator is growing drastically, and dividing by something really, really large would be equal to 0. This is a great property to remember and very useful. So in words, if the denominator gets bigger faster than the numerator, in this case, if it's constant, then the entire function is going to go to 0. Methods for solving limits at infinity. And this is for rational functions. So one would be to divide each term of the function by x raised to the highest power of x found in the denominator and simplify. 2 would be to determine the behavior of each piece of the function by evaluating each term as x approaches either positive or negative infinity. Your answer may be constant L, or it may be positive and negative infinity. If your answer is positive or negative infinity, remember that technically the limit does not exist. So to evaluate limits at infinity, divide the numerator and denominator by the largest power of the variable that appears in the denominator. That is key to dealing with these problems. And so it says find all horizontal asymptotes of f of x is equivalent to finding the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. In other words, limits at infinity describe the end behavior of a function. So we have two examples here. The first example says find the limit as x approaches infinity. And so for this, if you notice, if you were to substitute in infinity, which I know it's not a numerical value, but if you think about it, you technically would end up with infinity over infinity. And so that would be indeterminate. And so this would be infinity over infinity, which is indeterminate. And so the way that we're going to deal with this is going to be the limit as x approaches infinity of, and I'm going to rewrite our problem, leaving some spaces here. And if you look at the denominator, you'll notice that the largest degree that we have is to the second power. And so I'm going to divide all the terms by x to the second power. And it's okay to do mathematically as long as you do this to every single part of this expression. And so in both the numerator and the denominator. From here, I'm going to simplify this. So we have x squared over x squared, which is 1, plus 2 over x minus 5 over x squared, all over 3 plus 2 over x squared. And so from here, I'm going to ask what the values of each of these values are as we evaluate the limit as x approaches infinity. And so you'll notice that 2 over infinity, so 2 over something really, really large is going to go to 0. Likewise, 5 over something really, really large is going to go to 0. And 2 over something really large would also go to 0. And so this is going to be equal to 1 plus 0 minus 0 over 3 plus 0. Again, remember that the limit as x approaches anything of a constant is just that constant. So that's why the 1 and the 3 are still in our expression when we do direct sub. Those other expressions are going to be equal to 0. And so we get a numerical answer of 1/3. So we have another example right next to this. I'm going to go ahead and circle, and we'll look at this one together in class. The example right below this says a manufacturer determines that when X hundred units of a particular product are produced and sold, the profit will be P of X equals 4x minus the square root of X $1,000. What happens to the average profit when the production level is very small? So meaning very small, it would be approaching 0. We'll say X approaches 0. And it has to be approaching from that positive side, since production always has to be positive. It can never be negative. So I'm going to give it a little exponent of a positive plus there, so we know it's coming from the right. It also tells us average profit, and I'm only given my profit function. And so remember that average profit, and this is talked about earlier in chapter 1, of X is going to be our profit function divided by those number of items sold. And so our profit function is 4x minus the square root of x all over x. And this simplifies to being just 4x over x, or 4, minus the square root of x over x, which would be 1 over the square root of x. And so for this, the limit as x approaches 0 from the right of 4 minus 1 over the square root of x would be equal to, and looking at this, we're going to have direct sub. We'd have 4 minus 1 over the square root of 0 from the right. And so this is something different here. 1 over 0 we know is undefined. However, we are not evaluating at 0. We're just looking at what happens as it approaches 0 from the right. And so if you were to divide by something really, really small, so approaching 0 from right is a very small number. So this would be 4 minus something very, very, very small. in our denominator. So 1 divided by something very, very, very small would actually create something very large. And so this would be something like infinity. And then 4 minus infinity, the 4 is not important as compared to infinity. So that we can say this is just equal to infinity. And what this means, since we're talking about your average profit, and if it's a negative value, it's not a good thing for profit. And so this is a very big loss, which hopefully makes sense, since if you are not producing much, if your production level is very small, your profit should not be very large either. And so for in this case, it's a very big loss. Right below this, it says continuous means to have no breaks or interruptions. Informally, we say, can I draw a graph of this function without ever lifting my pencil? And so we have some examples of continuous and discontinuous functions. And so if you look at the first one, it's continuous. You can draw that graph without lifting your pencil. Likewise for the second one. The third one, though, you'll notice at 2 it is discontinuous because you did have to lift your pencil here and you did a jump. Likewise with the next one, it is discontinuous at 3 because again you would have to jump down to that other point and then come back to the graph. At the top of the next page, it says a function is not continuous if the graph of f of x has a removable point, a jump, or an asymptote. And so a removable point is going to occur when we have 0 over 0. Remember, this is our indeterminate form, and we can simplify. A jump is going to be from usually a piecewise function. So from a piecewise function, this would be where the left and the right side limits are not equal. And then an asymptote, again, is where you have a number divided by 0, and you can't simplify. So can't simplify. So the table right below has a picture of the graph, an example, along with the name of what we have. And note that some piecewise functions are continuous if the left and the right side are equal. So continuity at number C says, suppose f of x is defined on an open interval containing x equals c, then f is continuous at x equals c if these 3 conditions are met. So the first one is our function at c is defined, and then the limit as x approaches c exists. This means that the limit from the left must equal the limit from the right, and so those 2 values must be equal. And then the limits from the left and the right would be the limit as x approaches c of f of x would be equal to f of c. So this means that the limit would equal the function's value. So we have another example right below this that I'm going to go ahead and circle, and we'll look at this one together in class. On the table at the next page, these are continuous functions, and so you can see type of function, where it is continuous, and graph of an example. And so a polynomial function is continuous for all values of x. A rational function is going to be continuous anywhere where the denominator is not equal to 0. An even root function is going to be where that part inside the radical, the radicand, is going to be greater than or equal to 0. An odd root function is continuous for all values of x. Exponential functions, which we get more into later on this semester, will be continuous for all values of x, and logarithmic functions, which again we get into later on, are going to be continuous for all x greater than 0. So the example right below says find all the values of x for which the given function is not continuous. So it does say not continuous. And so for part A, says f of x equals 2 plus x over x times x minus 1. And this is a rational function. Again, rational is that fraction function. And so this is where the denominator is not equal to 0. So our denominator is x times x minus 1 is not equal to 0. So x cannot equal 0 or x cannot equal 1. So it's not continuous. So not continuous at x equals 0 and x equals 1. For b, it says f of x equals 3x squared minus 4x plus 8. This is a polynomial. And as stated up above, it says continuous everywhere. Part C says f of x equals x squared minus 36 over x plus 6. And so for this, it is not continuous, where the denominator is equal to 0. And so denominator is not allowed to equal 0. So we have x plus 6 cannot equal 0, or x cannot equal negative 6. And so it's not continuous at x equals negative 6. It's also good to note this is a little different than part A. Part A, we were unable to simplify our rational equation. But for this one, you are. The numerator would factor to x plus 6 and x minus 6. And the denominator was x plus 6. And these do simplify. And what this means, because these simplify and reduce, is that we have what's called a whole. And that whole is going to be at x equals negative 6, what would cause that factor to be 0. And so it's not continuous there because it is a whole. It's not a jump. It's not an asymptote. This would be an example of a whole. So the next example right below this is it dealing with piecewise functions. And so I'm going to go ahead and circle this one, and we'll look at that together in class. So the next thing we have is called the intermediate value theorem. And this says that if f of x is continuous on the interval from a to b, and L is a number between f of a and f of b, then f of c is going to equal L for some number c between a and b. And this is used for the existence of zeros. And so this says that if f of x is continuous on the closed interval a to b, and if f of a and f of b are non-zero and have opposite signs, so that means that one of them would be positive and one would be negative, and or vice versa, like with the signs, but one's positive, one's negative, then f of x has a 0 in the closed interval a to b. In other words, the function f of x must cross that x-axis, and so we would have a 0 there, or an x-intercept. And so yes, another word for 0 is an x-intercept. A useful application of the intermediate value theorem is to estimate the break-even point. Some problems that we have, it is too difficult to actually find this break-even point by hand. So this will allow us to estimate it and determine an estimated point for that break-even spot that we would have for our production process. The last example here, I'm going to go ahead and circle, and we'll look at this one together in class.